Okay, so today we're going to be talking about the tool chain in the application binary interface. Essentially, this is the last course where we're reviewing 373 or reinterpreting 370 in terms of 373. Sorry. This is the last time we're going to do review material that's focused on this class. Then we're going to go off to new material. Next week. All right. So announcements, homework 2 is posted. It's due Sunday next week. The lecture or the exam dates and times have been confirmed, so they're on the website. I put them on Piazza. There they are. Remember, we have 2 midterms earlier in the semester, and there's no final. All right. Any logistics questions? Yep.
Is it due 9/11 or that's Sunday?
I don't know. What does the grade scope say? I will double check then. Maybe I might have that wrong. Any other questions? A good question. Yeah.
Grade scope says the 11th.
Which is Sunday? Oh, Monday. Fine. Monday then. We'll change that to Monday. Whatever grade scope says. I'm not in charge, even though I set up grade scope. Don't trust me. Trust grade scope. Okay. Any other questions? Great. Told you I was going to give you a embedded system component of the day. This is the voltage regulator. Some people don't know what voltage regulators are. They are fundamental pieces to your embedded system, and you have to think about each one of your embedded system's components, whether it's a microcontroller or some sensor, needs some very specific voltage. The data sheet says, power me at this voltage. It doesn't say plug me into a LiPo battery and hope for the best. Promise, that's not what the data sheet says. And so voltage regulators are just usually, the simplest ones are 3-pin devices, ground, power in, power out, and all it's going to do is going to take whatever voltage you put into it within reason, and it's going to provide that voltage to your embedded system device. So when it comes to project time, you're going to want to make something battery powered. You need to have a voltage regulator in between. What they really do is, yes, they regulate voltage, but they're also very good at suppressing noise. And your embedded systems will have lots of noise on the power line because you have switching things that pull current, all sorts of weird ways to get noise into your power system. And the regulator will hopefully negate some of that and kill some of that noise so only clean power runs through. That's important, say, if you're having an analog digital conversion, you're trying to measure some sensor, you don't want your power line noise corrupting your sensor measurements. There are a huge variety of these things. In terms of, is the output voltage fixed or adjustable? Sometimes you put a resistor on there to define the voltage. They have different current ratings. They have different input voltage ratings. So if you need to power something, you got a battery, you got a microcontroller, you got to put something in between. It's going to be a voltage regulator. Any questions? Great. All right, so today we're going to talk about some tool chain stuff, go through some examples of the GNU radio chain, directives, labels, and we'll talk about the application binary interface specifically for the ARM Cortex-M4 that we're using. All right, so from high level, we have C, right? That is going to get compiled into something, into assembly. So there's a compiler that's going to convert it into not machine code, but in assembly, something that's human readable. That's the point of assembly. And then your assembler converts that into machine code. So that is the actual ones and zeros that are stored into memory. Now, when you guys use Cube IDE, a lot of that's just obfuscated away from you, right? You just push compile or run, and it all just does it underneath. But there's an important steps in between here to kind of understand. So, like I said, Cube IDE hides a lot of this. But what's important to also understand is that underneath, there's lots of different dev environments for ARM. You can use pretty much any one of these. The key thing is that underneath is something called GNU, right? So GNU tools are embedded systems tools and computing tools that have been open sourced forever, and they're the core of all, the backbone of all these IDEs. So if you want to get the lowest level possible control over your microcontroller, go look at the GNU tool chain. It is obscure, let's say, not well documented, but it gives you complete control. I had a project where we wanted to change the way, we had energy harvesting nodes that would be powered off RF radio waves, and we had a whole class of bugs and issues that only exhibited themselves when you were running off of harvested power. And so how do you debug that? Because as soon as you put your JTAG debugger on there, or your USB cable to walk through the code, it injects power and it corrupts your signal. Now you've taken this thing that was a bug that only exists on energy harvesting and added power, and the bug goes away. And so I had a student go through and rewrite GDB to actually have breakpoints that would inject or not inject power into it. So you can get all the way down to the lowest level of your tool chain if you want to go to GNU Radio. You won't have to do that in this class. We used to make you do that in this class, and all the students were like, I don't understand what this stuff is. That's fine, but it's important to be aware that CubeIDE is going to hide all these things from you, and you have access to them if you want. Okay. The last thing to kind of think about with a tool chain is you have some C files. You may have a library that you're compiling. You might have some precompiled assembly files. Your assembler is going to turn those into, and your compiler is going to turn those into object files. You're going to have some other libraries. And then your compiler GCC linker is going to take all those things, put them together. And as we'll see, remember, in your C files, you're going to have variable names. Well, you don't know where that data is in memory. Well, the compiler here and the memory layout, we call the mapper, come together and resolves all those links and turns it into an executable image, and you get two versions. You get a binary file. This is the actual binary 1s and 0 bits that get put into your microcontroller. Usually they also give you the option, or do it by default, you get a disassembled list, and this is what you jump through when you debug. So if you're going to debug something and walk through your code, your IDE actually is using the disassembled file, and you're walking through your code, and at certain breakpoints, it will show you what's happening by basically pointing you to the disassembled file. So that's what's happening underneath CubeIDE. Any questions? All right. So we can look at an assembly program. Assembly programs, you have some, at the very beginning, you have some directives. These are not necessarily, this is not necessarily code. This is directives tell the assembler what to do. Okay? They're like pseudocode for how the program should get laid out. You have labels. These are also not code elements. They are just points, right? If you're looking at assembly, this is not a memory address. It hasn't been converted to a memory address. So these labels help tell the program where to branch to. And then you actually have your code itself. Okay. So we'll go through these elements so you can kind of see what is underneath at the lowest level, what the assembler is doing here. So you have your global start statement. This exposes the symbol globally. We have this thing called a directive. This is a space. Let's see if I have a thing on this. Yeah, space is, you can go look into the documentation online for the manual. Space just fills up location in memory with zeros. You have a little padding between your code. You may need to have that for various reasons. Space is a directive that allows that to happen, ensures that happens. Byte is an expression that allows you to put data into a particular location in memory. Let's see, we have, you guys have seen some of this in your homework, but you have different move commands. So we have move, right? It takes you, especially move immediate or move register, allows you to move data around the registers. Move wide lets you move the top, and lets you move the bottom, the upper 16, and move top. Wait, did I get that wrong? Move wide allows you to move the full thing, right? And then move top is just the top half. That's right. All right, you have these other weird directives here. Now, if you think about it, we have some data. We define some data. It's in there. It's going to have these bytes here. So you're going to have hex 12, dec 20, hex 20, -1. But you don't know where that data is. So we've assigned that a label. So data is the label. And now we're calling that label here in assembly. And we can't, in a move option, can't move 32 bits at a time. So we're going to use lower and upper as directives to tell move, take the upper 16 bits of what's in data and the lower 16 bits of what's in data and put them into R1. Okay. Yep, and there's, yes.
So when you're moving to a register, you're like move R0, 0. You're only moving 16 bits into R0?
You can't, think about the immediate. You can't put 32 bits in there. Okay, so it's going to pad, so move, just the move command will put 0 and put all zeros in there. Okay, So the top is just going to be assumed to be 0. So there are certain numbers you cannot get to with the move command. And so this is a way, especially when you're talking about data in memory, that you can move 16 at a time. This is essentially like move immediate, although it's move the value that would be there. Okay? Yeah.
Which data are you transferring from? Is this hexadecimal 12 or is 20?
That is an experience for the student to find out. But yes, you should be, it's encoded there, so hex 20, so 0x would be the way to express hex. If you just see a number there, it's 20, right? So that would be dec 20. You got hex 20 there, and then you have -1. So it would be 0b if it was in binary, 0x for hex, and nothing if it's in dec.
Oh, but I mean, like, there's a bunch of data. There's like 4 data in total. How
Yep.
do you know which one of them should be put in the lower 16?
How big is that data?
The bytes.
Yep. So if we go back to definition, it's going to sequentially put bytes of data into memory. So that's what the byte command is doing, is putting this byte in where? Right, so we're starting at memory location 00. We're taking 8 bytes worth of space. Then we're going to put data, 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 data right in those locations in memory. Other questions? Okay. Yep, upper and lower. Okay. We looked at this last time. You have load from register. So we're going to take the address that's in R1 and go to that address and put it into R2, but we're going to offset by 1. And remember, this is a byte operation. So we're only going to take a byte of data. We're not taking we're not taking a 32-bit word. And then, we talked about these. So these are byte-wise operations. And then we have compare. So this is going to compare these values. How is it, and then it's going to see if this value is greater than that value. And if it is, then it's going to, what's it going to do? Compare it, and it's going to go to branch. Then we're going to branch to loop. We're going to keep going around. If it doesn't, it's not going to do this. It's going to go to dead loop. I think that's right. Right, and so this is also a concatenation of branch not equal. So if I messed up. So this is just going to make the comparison. The comp sets the flags in the ALU. Yes.
Could you further explain the .byte? Like, what would the contents of our register be?
From .byte? Yeah. .byte is defining in a place in memory what data should be in that memory. So it's a directive. It works on, it's not part of the assembly code. It's telling the assembler, I want you to put the following bytes in the location in memory. Yep.
How would we be able to find the memory locations where the byte directives stored those values?
Aha! That's a great question. So your assembler, is, as we'll see, is going to resolve the labels. So, there's no loop label inside the binary file. Right? That is a memory location, okay? So this points to a place in your code. So data will be replaced with a memory address. Now we happen to know, we'll walk through this example in a bit, but it'll happen to be 8 bytes, and then there'll be data will be right there. But the compiler, this could be part of a bigger program, or in your assembling multiple files together, and then you don't know exactly where it would be. So it'll get resolved by the assembler.
For the load command or instruction, so it would just increase the offset. It would increase the value of R2 by 1. So would R2 just...
Which type of indexing is this? Does anybody remember? Yeah. Right. So it's going to offset the value in R1, right? But it's going to do it after it goes and does, it gets the data and places it in R2. Yeah?
So does space allocate memory or?
Space and bytes are separate commands. They're separate directives. Space is allocating, especially white space, unallocate or all zeros for a particular memory location. We're going to do, it's going to start with space. It's going to do 8 bytes worth of white space or zeros.
So there's like nothing in that space before it gets to that byte.
Correct.
So when we're using -1 with
Yes.
byte, are we filling those 8 bits with all ones using 2's complement, or how are we signifying it's a negative number?
2's complement.
2's complement, okay.
Yep.
But the actual bits are just set to 1, and from other perspectives, it's just 8 ones. Like, are we always, or do we always work in 2's complement?
Yes. Well, your assembler, seeing that you denoted that to be -1, is going to put it into 2's complement.
So if I said 0xFF, it would have the same result.
Yes.
Right.
Good. Yeah.
I just wanted to clarify with my question. I wanted to make sure that R2, since it's loading, R1 is loading to R2, correct? But what byte, I guess, data we're storing to R2?
Okay, so R2 holds the location, the memory address of something, okay? It's going to go to that memory location and pull out some value, and it's going to place it in R2. So your question is, where is R1? Well, R1 got defined up there.
No, I get that. I mean, like, what does R2 have?
Which byte is it? The last byte of data or the first byte of data?
Those are put in sequentially.
So which byte does LDR byte?
Well, what's the address? So if that is going sequentially, the first address is going to denote that. Remember, this instructions, this is byte addressable. So you'd have to have, each one of those things has got a different address, and you're going to load in that byte and put it into this register. And it's going to do that first byte, and then it's going to increment the address, next byte, increment the address, next byte, as it places that into memory. Does that answer your question, maybe?
Yeah.
Okay.
What if the like hexadecimal 12 is like exceed the size of the byte? What would happen in that case?
I don't know, maybe your assembler will throw an error.
Oh, okay.
I guess it could. Either assembly is going to throw an error, or it might. Oh, it's only a byte command. I have no idea. So let's assume the assembler will throw an error, or it will just truncate. One of those two. Yeah.
Okay. So if I give it a hex value, sorry, never mind. Bad question. If I give it like, does the assembler assume you always need 2's complement? I don't know what 2 to the 7th is, but if I try giving it 2 to the 7th, will it put in 1, 1, 1, 1, 1, 1, 1, or give an error because it's supposed to be 9 bits?
I don't know.
You don't know.
I don't know. Assembler does whatever the assembler does.
Okay.
What other questions do you have? Yeah.
What's called as the least significant bit or least significant byte, right?
Correct. It'll do this one first. This is byte-wise. This is not word-wise. So this is going to put the first byte in, then increment the address, second byte, like that. Yeah.
So if I had a second byte command, would it append to the previous byte command, or write like 12?
So if you did byte 12, byte 20, byte,
Yeah, like if I had a second byte command,
yeah, it'll just do that. It'll execute that command afterwards.
so it would append it? Like
Yeah.
append memory?
Yeah. Yeah, I don't know, appending is a weird phrase, but yes, it will.
It will keep incrementing
Yes.
forwards. It won't
Yes.
go back to 0.
Right, because byte has no location associated with it. These are directives that are saying, do this right now in this memory location. Yeah. Whoever.
Can you explain one more time what the move and move T command do for R1?
These two?
Yeah, we'll just type that out.
Move W. Moves the upper 16 bits. Okay, it's telling you that because it's got the W, it's the hint. And then move T, moves the top half. Wait, that doesn't make sense. Let me. What are those values? Those are the data, the immediates. This is an immediate that's held in data lower 16. So in data, you go to the lower 16, and you're going to go and move those into R1. So it's defined here.
Sure, so that's hex 12 and, I guess hex 14.
Yeah, we'll go through it in detail, I promise.
Yeah, I kind of have a similar. So is data referring to the address where those bytes are stored, or is?
Yes, it's a label. Yep. Yeah.
Why we are using lower 16 and upper 16? We cannot just put the 32 bits.
No, because your commands, your instructions are 32 bits. So how do I put a 32-bit word into a 32-bit instruction?
More space to say this. Okay.
I just run out of space. There are many ways to do this. That would, yeah.
So just to understand, because I also saw it in pre-lab, we go into data, we grab the lower 16 bytes, put it into R1, register 1 in the lower 16, and then we do the same thing, but just the top line.
Yep. All right, let's move forward. Well, any last question? We'll have this be an exercise for you guys. You guys can work on it together. What other questions do you have? You can obviously work with each other. And then we'll walk through the code.
Wait, sorry.
Are they also?
0x12.
And as a reminder, the slides are all online. If you want the definitions for byte, it's right there.
Oh, yeah, it's on the slides.
There you go.
Project haven't even started.
Thank you all. You guys run out? You guys are in out as well? 2, 3. All right. Yep.
With data here, is it?
You mentioned that we it's 14, 9, 16 plus little and minus 1 is
Yeah, so you can think of it as 14. You didn't already. Where you just randomly copy and paste off the video.
I just want to make sure, so by instruction, you would put like 0x12 and the first byte, the next byte, and then the different amount of it.
Right, so the byte command works on byte, not on the whole word.
Okay, yeah, that makes sense.
So just as a reminder, the byte command works on each individual byte individually, not on the entire word. Okay, so it's going to do byte, so it's equivalent to say byte hex 12, byte 20, byte hex 20, byte -1, right? So it puts it in one location, increments, next location, next location, next location. Yeah. The directives are pretty simple, so not really. And there's other ways to accomplish that goal if you wanted.
No, so this is like a code network. So there's always 6 units for being an immediate. So when the register is 32, so you have to do it twice to load the entire part to register. Yeah, it's like separate.
So R1 is 1, 2, 1, 4,
Yeah.
And registers get 32 bits.
So we also
It doesn't hold it all. 32, 8 times
we know what's
now I
in this address.
This is the value add data.
Yeah, I don't think we I think we should figure that out. Yeah, when I forget. It's just loading the. R2 is the destination register.
Where is R1? And then
Yeah, we just plus one. Plus one for R1. Yeah, it didn't give us any information about characters. We don't know what's in this address, right? Yeah, I didn't see it.
What do you guys think?
It's just, I think we can assume it's zero. I'm saying it's probably zero.
I guess there's something
Probably, I don't know. He will show the answer. Oh, this is just a for I equals 0, I plus, yeah. Yeah, so.
All right, so
Answer is
one bit of confusion is data is an address. So at the end of this, you have the address in R1.
Yeah,
sorry, what are you saying?
So data is an address, right? This is data. This is the address right here. So at the end of this interaction, you have an address in R1.
So R1 is now completed as
Okay. But I don't know what that address is before I compile. I have no idea what it could be. So I gotta represent it some way.
Oh, that's why you have this data byte.
That is the data itself.
This is the address, or is it the address?
Sorry for repeating again. So you're
Data is
saying. Right.
Label represents an address.
So it's going into compare our data,
Yep.
and then the data points to this.
Correct. So then when you go to do this command, where's that location? Where'd you get the address from?
It's like
This is data, whatever data it is. Whatever that address is for data.
This area here is,
Yeah.
and then when you get the byte of R1, it's actually this.
And R2 is available in this form.
Well, add yes, R2 is about
First byte of this one.
Yeah.
Okay, thank you. Yeah.
So R1 is,
So R1 is like a random number.
yeah, we don't, that's why we're not asking.
It was assigned by the
Yeah, so R2 is 1, 2, 1, 4.
What do you think?
Okay, that's a lot.
What would happen if you did
Yeah, I think that's all the main takeaway of this. Of this.
And then we also need to do something else.
Yeah.
So let's go off of a lot of our memory space.
I don't care about the others anymore. As long as nobody's fighting.
The end is just the end of this function, right? The end isn't the end of the program. It's the end of the function.
R4 is the sum of that stuff, right? Because it adds like we have to kind of like think back and R2 to R4, right?
I felt like, because it's loading the first byte of the
All right, does anybody have an answer for R0, R2 they want to share?
4 is FF.
Okay, what about, anybody got R4? Yep, all right, good. Let's walk through that and make sure we see how that works. All right, so here is an online ARM v7 simulator that kind of works. It's not exactly STM's flavor, but it will do everything correctly if we don't look too hard. We have our code. We're going to we'll show the disassembled file, and then we're going to show memory locations. If you use this, I've broken, normally it represents, every line is 4 memory locations, or 4 32-bit words. I've just broken it out to 1. So each one of these is incrementing by 4. Okay, so there's the code. Oh. I think learning happened, I don't know. All right, so we've compiled the code into assembly, and so some things have happened here, right? This is a different representation. You can see the binary, the values here, and you can see modified code here. In fact, let's see, like data, right, now has a value. No, it doesn't have a value yet, sorry. Don't worry about that for a second. Okay, so let's walk through this code and see what happens. We're gonna start at, in memory locations. Let's see if the directives work. So first we had 8 bytes worth of space. So that was defined to happen at the first location, right? This is the first location in memory space was operated on, and you put in 8 bytes worth of zeros. And so we see that here, okay? And then so that's here and here. And then we said byte. Byte was a command that was instantiated. And in this particular thing, we got 12, 14, 20, FFF. So here the assembler went and figured out, you put -1, it turned that into 2's complement, and then you can look at all of this. This is all in hex. So 12, I think 20 is 12, right? Or no, 20 is 14 in hex. Okay, so there's the memory locations. So it's been put into memory. Now, let's see here. Now we're at address C here, and this is the actual instruction, right? Address C is this instruction here, which is move. That just happens to be the encoding for move, okay? So let's walk through this. So first, we're going to, come back. So step into this. We've moved 0, 0 into R0, R4. That's just in case there was already, here's a register space, sorry. That's in case there was something there from beforehand. Now we're going to move the lower part of data into R1. So we're going to do that and that. And the top is all zeros. Where is that location? That is that location memory 8. Right? So 8 was the data is an address, is a label. So labels are addresses, and when we compiled it, it got resolved into a memory location, which is 8. So now 8 has been moved into R1, and we can see that up there. So 8 is here, okay? Feeling good? All right. Then now we can go through our main loop. We're gonna load in some data. Where are we gonna get the data from? We're gonna get the data from the address that happens to be stored in R1, and we're gonna place that data into R2. So now we've gone, and it's a byte-wise operation. So we've gone and grabbed, over here we've gotten 12, and placed that into R2, byte-wise. What questions do we have? I'm sure there's questions out there. Yo.
Do you mind explaining again why R1 is 8?
Sure. When this code was written, we didn't know where the data was. Okay? We only knew that we've labeled the location of the data stored by the bytes. We have a label for that. And so to get the address of where those bytes are, it got resolved. So we're saying that we're going to take the lower 16 of data, which is this address, put it into R1. Then we're going to take the upper 16 of data, which is the address, and put it into R1. So R1 now holds the location of data, the address, which is 8 up there. So address 8 is then, and then the bytes have instantiated that data into that memory location.
So it's just arbitrary?
Oh, what the value is? Yes, it's arbitrary because this code probably is could be part of a larger program, could be multiple files. And when you wrote that file, you didn't want to have to think about, oh, where's everybody else putting their data? You just said, put it at location data. The assembler did what's called floor planning, where it says, I have all these files that need all this memory allocation. I'm going to place it in memory. It's kind of like a floor. We're going to place it down. And because this is a simple program, we could go and calculate where it's going to be. The first being 2 locations, memory locations being all zeros because of space, and then 8 being the next location where byte was going to go. The byte was going to place this up. Yeah.
It's storing, so in this case it stores 12, right? It's register 2.
Hex 12 into register 2, yes.
And it's just capped as hex 12, right?
Hex 12, yes. Because we defined it to be hex 12 here.
And everything else gets written as hex?
Everything in this simulation is all hex. And same for cube IDE. All right, let's go forward the program. So here we're going to add, let's see, the value that's already in R4 plus R2 and place it into R4. That's equal, that says 12 plus 0, x. And then we're going to increment R0 by 1. So we're going to add 1 to the value that's in R0. It's 1. And then we're going to compare, is R1 equal to number 4? And it's not. So then we're going to go forward. This is not equal. Okay? So that flag was not done. In fact, we can see the flag here. This is the program status register. Here, those are showing you the flags right there. Okay? And then we're going to go back through our loop. And then the address, I should have pointed this out, the address here, it used to be 8, now it's 1, or now it's 9, because when we did our load instruction, or load byte, we did post indexing, which added 1 to the 8, incrementing that value in the register. So the next time we go through the loop, we're going to grab another value. So let's go through here. We've gone and gotten 14, hex 14, out of memory. Placed it into R2. How are we doing? What questions do we have? Okay. And we'll step through a little bit more. We'll go quick. Keep getting values out of memory, adding them together. Let's see, what are we getting to? One of the last loops here. 4 is compared, 4 equals 4. Let's see. So we should see this value here change, right? So now the status flags have changed. Fantastic. And then when we do our branch, not equal, it's not equal. We're going to go forward, yes.
So when I got that 4th byte, that -1, that was translated as FF,
Yep.
it didn't treat it, when it added to R4, it didn't treat it as -1, it treated it as FF.
That's true. You did not tell it to do a signed add. You or in assembly have to tell it how to interpret that data.
So if we were adding very large numbers together,
Yep.
and R0 overflowed,
Right.
would it just overflow?
Yep. You get a flag that says overflow. It's one of your flags, so you could do a check to see if you're concerned about that. And then there's other tricks you could do to put that into like a 64-put value. You could split that amount across two registers, there's ways to do that as well. All right, and then we'll step through, and then we're going to go to dead loop here, because this was true, or this was not equal, this was equal, and you're gonna go, sorry, that was equal, therefore you didn't jump back to loop, you went to dead loop, and then you just stay in dead loop forever. Why do you want to do that? Or what would happen if you didn't stay in dead loop forever?
As soon as you hit next, you would end the program and everything would reset.
No, it'll just keep going. It's going to say, fantastic, I'm so happy here, I got my program counter, I'm going to go to 31 or 34. Then it's going to start executing this line of code. And then it's going to start executing whatever that line of code says to do, whatever 00 says to do, it's going to try and do that. And then it stops. But the end here is not end of program, not end of execution of the CPU. It says end of this file. That's all it's saying. Yeah.
Well, but if you keep looping, I guess, wouldn't you be
Yeah, it could be an infinite loop. It's better to be in an infinite loop that's controlled than uncontrolled trying to execute memory space. This is a small little thing your compilers will take care of in a sense. But yes, you want to be in a while loop. You want to be in a known location rather than having your plane do weird things where unintended. All right, what other questions do we have? Okay. Great. You answered this question, that question, you got all those right, fantastic. All right. How much time do we have? Okay, so let's go on to the application binary interface. This will be helpful for lab this week. And then that will wrap up the kind of 370 review. All right. So the application binary interface is a contract between programmers where you can share resources, right? So if you're writing some functions, you don't want to have to coordinate with some person to say, okay, which registers are you going to use? So we're going to go in through and have a interface or a spec that says, here's how we're going to share these things. All right, well, I guess I've already answered this question. I was going to say brainstorm, but I basically already answered it. Okay, so some basic rules. Subroutines, right? Functions must preserve these registers, so R4 through R11 in a stack pointer. Arguments can be passed into the lowest registers, so R0 through R3. You return your values in R1, and R1 and R2 if it's a 64-bit value. Okay? This is the agreement. And you can allocate space on the stack as you need. So if you need extra space or you need to use those upper registers, that's fine. But you are responsible as the programmer to reserve those registers, preserve the value in those registers. So if you need, say, register R4 and R5 for some interesting calculation, you're going to take those values, put them on the stack, do your stuff, and then replace them so that the program, when you return to main, has the correct values in there. Oh, and there's a small error on this slide on number 1. I'll clarify it next, but it really doesn't affect you, I promise. Let's see how that works. Okay, so these are not to be saved, right? So the caller does not have to, or the callee does not have to save these values. They are scratch space. We have these registers highlighted in red. The callee expects those to be saved. So these values the function cannot augment. There are some minor exceptions here, which get students every year. R9 is specifically for our architecture, is for static base registers and threaded registers. We never use that stuff in this class. Like your compilers are doing that stuff underneath. In the V6 architecture, it's just a normal register that you can use for whatever. But for this case, don't modify that register, okay? It's not available for you to use. And then lastly, there's this is scratch space for interprocedural calls. Yes, you could consider that to be calling a function, but this is really used with interrupts, which we'll discuss in a couple of weeks. So ways in which interrupt can pass information back and forth between the main program and the interrupts. That's what it's really for. All right, so if you're going to write functions, you have inputs, R0 through R3. You can concatenate them in any way you want. There's some subroutine, and then you have your ways to output them. Technically, you can go through and put data all the way in R0 through R3 if you want, although the convention is usually always, the convention is always starting with the lowest register and then working your way up as necessary. So we can see, any questions so far? Okay. So we can see some of that in action here. See, so calling a subroutine, you can do branch to a label. So here you're going to, basically you're just saying, I'm going to branch to the label plus, you're going to branch to the label, you're going to set your link register. You got to know your way back. So your link register is going to be PC plus 4, and then your new PC is going to be labeled. So that is just a place to store your return path back to the main program. Same with branch. Let's see, this is an example. So it's an example of a non-ABI compliant function. Here, if you go through this, here's foo, right? Foo is going to modify R4, but yet this add would be incorrect, right? So if you're going to add 1 to R4, this caller function had assumed that R4 would have been preserved with 100, but instead this thing modified it to be 10. So this is just an example of this programmer never expected that error to occur because this violates the protocol. All right, so let's go, we'll walk through in a more detailed example. We'll do a simple sum of squared function. So here you're gonna have a function that takes 2 variable inputs, write this in C, and it's gonna return the sum of the squares. Okay? We'll make you guys do that, but this would be the, essentially the assembly, or this is the C written out for that, and then there's the assembly. So let's walk through this example. In this example here, right, this is just how the C would correspond to the assembly. Basically, you're passing your lowest variable into R1, your next variable gets pushed into your lowest variable gets pushed into R0, and then your next one into R1, and then your return value gets placed in the lowest value register, which is R0. Then you'll branch back. All right, so we can walk through this example in a little more detail. So this is supposed to be your assembly code. This is your register space. This is memory. For the sake of this thing, I've switched the spots. Normally I think about it as you have addresses and then you have data in those addresses, and here I just swapped them around so you get confused. And these are the instructions that are in these memory locations. So our program counter is pointing at whatever this is, memory location 8, blah, 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 128, okay? It's pointing at that thing, it's going to execute that command. So here we're going to move the number, the immediate 3, into R0, and we've gone and modified that register. Then we're going to increment the counter, or the program counter. So now we're gone off to this next value here, incremented by 4. We're going to move 4 into R1. Now we're going to branch. We're going to branch to a location which is SSQ, so sum of squared. Normally this would be, there'd be a memory address here, but here I've just labeled it, so now we know where to go. So before we branch, we need to store the next instruction in the link register. So when we return for that branch, we know where to go. So here, we're just going to take that value, get stored into, that address gets stored into the link register, and then we go and branch to that location. Okay, so now we've going to multiply, and didn't fit all in there, but we're going to do this instruction here. We're going to multiply R0 by R0 and put it into R2. Then we're going to go and do the next instruction. So R1 times R1, put it in R3. We're going to add those values together, put them in R2, and move that value to R0. Then when we return back to our main function, we're going to take the link register and put it into the program counter. So that's branch to the link register. That's the nomenclature. So we're going to put that value there. and now we're back to this location. So this was before we left at SSQ, which was at 103, but because we incremented by 4, the next value is in link register. When we return, we go back to 11 or 134.
So the difference between BL and BX is whether it's the link register?
Yeah, I think it's BX, this is for the link register. The other one is just for any branch that you're gonna do.
So like BX wouldn't save the instruction after it to the link register?
No. Yeah.
Branch normally uses labels too, right?
Correct.
But is LR a label? Is it a register?
This is
Is it labeled for register, I guess? Like other branch instructions use it?
this. You're branching. BRX is branch to register. So you're branching to the register defined by this. So you could branch to R3, anything else, I suppose, but you're going to do the link register specifically. So it'd be a branch to a label versus branch to a register. Good question. Yeah.
So I'm just a little bit confused on what happens on that instruction for BX and LR.
Sorry.
So it jumps to the link register, and the link register already had the instruction move R to R0.
So are you talking here when we execute this?
Yeah.
So it's going to take the value in the link register and put that in the program counter.
Oh.
Right? Because that its goal is to go back to this memory location. We're exiting this function, so we have to go back to the next instruction after we call that function. So that's to move R to R0, and so it's going to take this value and place it there.
And then we exit out.
Yep, that's just the process of exiting. Now we're going to go and execute that instruction. How are we doing? I think half the lab or half the class is like, I don't believe anything this guy says. Super confusing. The other half is kind of like, yeah, this is horrible. Two extremes. Okay. Any other questions on this example?
I mean, we have seen this yesterday labs already. So.
Okay.
Yeah.
Well, we're going through. So you're saying the labs are a little bit out of sync?
Yeah.
Okay. That's tough. Okay. Well, I mean, it's tough for me. Sorry. It's not. What I meant to say is in my brain, it's very tough to get all the content done in time. I apologize for you guys for not having it sunk up. Okay. So one thing to keep back is that in this example, sometimes depending on how those instructions were coded, if they were 16-bit or 32-bit, you would have been incrementing by 2 or 4. Okay. However, in reality, the PC always increments by 4 every time. It's just that when you do the fetch, then it's going through and deciding whether it's going to be two 16-bit instructions or one 32-bit instruction. Okay. So if you're looking through your code, you say, I'm going to the next instruction, but it's a 16-bit. Why did I jump increment by 4? It's always incrementing by 4. That's how the PC works. Other interesting pieces of information here is that the least significant bit of the link register is always 1 for the ARM Cortex. It's telling the processor what mode to operate in, whether it should be in thumb or ARM instructions, but your particular microcontroller only does thumb. So because the lowest number of the link register doesn't matter, because you're always incrementing by 4, they're reusing this digit to remind the processor what mode it should be operating in. And again, for your particular processor, you're only going to be doing thumb. But if you, I suppose, if you wrote, if you got a file from somewhere else that that was encoded in ARM, then it would tell the processor basically, and then you would basically throw a fault like I can't run this program. Okay. And then when you guys are going through trying to look at your code, this is right. When we write code, we think the minimalist amount of work in some ways. We would go actually put it through like this simple function turns into all this nonsense, right? Because the compiler is trying to be as safe as possible. It's trying to use the stack pointers. It's trying to use everything as safe as possible, frame pointers and stack pointers to ensure that there's no issues. So you can turn that stuff off. You can go to different compile options. So this is, you're going to omit frame pointers reduces the code size. And if you go to optimize 0.1, right, the most optimized you get, then you actually get out code that makes sense. So I'm just telling you, if you're ever in that point where you're trying to debug your code in the disassembler, you'll see wild things in there. Now you might know why that is and how to handle it. And you can see that they, as a particular function was a little optimized a little bit more than ours, but that's just a detail. All right, so let's look and see how we work with stacks. So, oh wait, let's ignore that. All right, so that was the issue, the non-ABI compliant routine. This is an example of an ABI compliant routine, a little bit out of order. How stacks work is that you can push to the value, you have some register, and you're going to push that up to the stack. So the stack's at the top of memory. If you remember your memory layout, there's actually a bunch of reserve space up there for ARM to have control of registers, or memory space. And so you're just below that, but technically you're at the top of the most available memory. So you're going to put your data there, and then it's going to descend down the stack. So you're always moving down. One thing to think about is that you can push multiple values, register values, but it's going to reorder them. This is because hardware is going to go by ascending order of registers, not the order you put it in. And it doesn't really matter as long as you, as you're pushing and popping, if you use the same variables, it won't matter. But I'm just reminding you, you can get into interesting errors where it's going to reorder for you. It's basically because they're trying to really optimize how much work can get done in a single cycle, and it's much easier to go sequentially through the registers and load them into memory rather than popping back and forth up and down. So your compiler obfuscates a bunch of those details away from you. Pop is the opposite. Pop is going to take the values out of your stack and push them back onto the registers. Again, it's also reordering. It orders the same way essentially as it does for pop. So you won't be making mistakes if you just use the same number of variables. So here, examples. So push, here's the stack pointer is pointing at some location, and you're going to push those values in. It's going to go from the highest value, register value in decrement. So here you put R3172, you put 7321. It goes in increments first and then puts the values in. So stack points to the last valid data that you have. It's not that when you push the stack pointer, the first location is not where your data is, it increments and then goes down. Same for pop. Pop points at the data that's actually valid, then it's going to increment, pop that off, going upwards, and then it increments its stack pointer one more extra value. So it's valuable just to remember that essentially that offset off the beginning. We didn't have time to talk about it in your last, I think, 2 lectures ago, but so I won't ask you this question, I'll just give it to you. But multi-word store and multi-word store and multi-word load, there is a variant that's the same as stack and push. In fact, if you wrote assembly with that, your compiler will just replace it to push and pop, depending if you're using your stack pointer or not. So there's multiple overlaps between commands. But that's not really that important, so we're not going to test you on that. Let's go for it. Okay. So how are we going to use the stack and subroutines? So you can imagine if you go and you call a function, and then that function calls another function, you have to preserve your path backwards, right? So you go here, you go to this new location, you put your link register, you put the return location in your link register, but if you go to another location and put that return address in the link register, you're never going to figure out your way back. So you're going to have to, at minimum, push your link register, but there's probably other data you're going to have to push as well. So we'll walk through that in more detail. All right, so in this example, we're going to do a subroutine which calls a subroutine. This is quad. It's basically going to take, quad is going to go and square some values. It's going to do that twice and return it there. So here you're going to have something raised to the 4th by raising that value, squaring it twice. Okay. All right. So just thinking about what that path is going to look like. So let's go through this example. All right. we have assembly code, we have instructions in memory, we have our stack, which is way at the top, okay? We have a stack pointer that's pointing to some open address. We don't know the data in it. It's never been defined, it's just pointing at that location. And then we have our program counter, which is set to 800138. Okay, so here we're gonna go and move 2 as an immediate into register 0. Now we're gonna call, we're gonna branch to quad. So what do we have to do when we do that? What's gonna happen first? Yeah, we're gonna move the link register. That's the next instruction, right? And then we're going to change the program counter to the address, which is defined by quad, okay? And then here, because quad's basically, the first thing it's gonna do is this, yeah.
Why is the stack allowed to hold so many bits? Like, isn't it like other memory where we can only have 2 bits at a time? Oh wait, it's
Incrementing by 4.
Okay.
Aha! ARM got you. All those smart people at ARM are tricking you again. Good question. Okay, so where were we? So now quad is going to call this, quad needs to call square, right? But it needs to preserve, part of its ABI compliance is it needs to preserve the link register so that when it goes back to the main, it can get there. So here we're going to pop, or push, sorry, link register up to, sorry, I guess it's already done. We're going to push that up to the stack, okay? So that the value of the link register is on the stack, yeah, 140, okay? We're going to go forward. We're going to call this function, which means we're going to put that value, the next instruction, into the link register. We're going to jump to that instruction. We're going to multiply R0 times 0, place it at 0. Okay, we've taken 2 times 2 is 4. We're going to branch out of that, which means to do that, we've taken the link value in the link register, put it in the program counter, and that pushed us back to, where are we going? Back to this location here. Okay, we're going to put the next location in the link register. We're going to multiply 2 things together. Great, it's 16. Now we're going to branch back to the link register. So we're going to take link register, put it into PC. Great, and then now we have to return. Now the goal is we have to get ready to return from this function back to main. But where is the link register? This link register would be the wrong address. That's the problem, right? So we have to go get the correct link register from the stack. We're going to pull that down, place that value into the link register, and then we're going to, and when we pop, right, we grab the value and then we increment the stack pointer. So the stack pointer is no longer pointed at 1FC, it's pointed at 200. And then now we're going to branch the link register, and we're at the end of our program. What questions do we have?
So when we're popping, we're not like clearing the memory. We're just basically leaving it there.
Yep.
Eventually we'll overwrite it.
Yep. So this is a small little microcontroller. We don't have memory management, garbage collection, any of that stuff. So you can imagine that there could be a memory leak. If you had some adversarial program on your microcontroller for some weird reason, then you could leave your keys up there or something. There are technically ways around that, even on this microcontroller. There's threading modes, but we're not covering that in this class.
If, like, in theory, you have way more registers than you have to do with, could you put the link register in, like, one of the R4 to R11 instead of putting it on the stack?
You could, but now your job is, as the Callee function here, you have to preserve that value that was in R11, right? Because the main may have put some data there.
Yeah.
So you could store it there, but what are you going to do with that value? You got to put that somewhere.
Okay.
So I guess you could have said, because you never used like R3.
But don't you always have to preserve it because it's to make it ABI compliant?
Right, you always have to preserve it. So you can preserve it somewhere else, but you might have to preserve something else. You could go and put it, I guess, in R3 and put it back. It's just that's not the convention.
Okay.
So if instead of, like, we push LR, if we pop R0, does it store the value of LR in R0? Or is that how the...
I missed it. Go slow for the old guy.
In the previous example, you had like push R1, R2, R7, whatever.
Yep.
And we popped in a different order and
Ah.
worked.
Yep.
So is pushing and popping register dependent, and there's some like tracking on the stack of what register you pushed from? Or can I just like pop into any register and push from any register?
Yes, you push and pop any register you want. Okay. The order, if you do a pop with multiple registers in it, it's going to reorder those. So if you wanted to do R7, R3, R2, R1, it's going to reorder that, but you could do pops independently if you really liked the order in which they were in the stack. If you don't care, then just use that pop function with all those variables. Got it. I guess the best way to think about this is you're going to pop multiple things up to the stack. Whatever you pop up, pop back, right? If you put 4 variables up, get those exactly the 4 variables back. If you're trying to split them up and say, I only want to pop 2 now and then 2 later on, now you have to keep track of what the assembler is doing. That's too hard. Just do individual pops then. Then you know exactly where they are in the stack. What other questions you have? I can't tell if I went too fast today or too slow, but we have extra time. Feels weird. Okay. Hold on. We're not done yet. All right, we'll recap a little bit, then I'll let you go. So we talked about the compiler, assembler. I think it's valuable to understand that toolpath, that one slide with all the arrows pointing. How do all these things get pushed into an executable file? And knowing the difference between binary and your disassembled data is important, right? And what the functions of those are. Understanding, I don't expect you to go read the manual for directives. It's painful, but you need to know what directives are and when you need to go look in the manual. Knowing that labels will get resolved when you do your assembly, that's important to understand how that works. And then just keep in the back of your mind, 5 years from now you're at some weird startup that's doing something and you want real control over your assembly or over how your files are managed on your MCU. The GNU toolpath is the way to go. So, and the application binary space is really the things that we really care about here are which registers are Callee safe, how the link register is used, and how the stack pointer is used. All right, with that, we'll end. Oh yeah, can you turn these, turn your worksheets back in? How hard did you get?
Are you allowed to use labeling?
Yeah, that's what, yes.
Well, lower and I mean, it's basically
That's the problem. It has to be a value that's in R4. So you can put that in the compiler and it'll just get it. Sure.
I was just reading up on the ISC. I think I wrote a mail to like a few days.
Oh, my apologies. We have a paper deadline on the 14th, and I have trying to compartmentalize my brain.
Let's start on comment next week. Yeah, really interesting the work.
What are you excited about working on?
Better software development, and yeah, EECS sounds really interesting.
So what we'll do
with the projects and all, so I mean, whichever would be potentially there any
So what I'll do is after, also none of my students have any space for thinking about anything, so I'll follow up with people and then we'll make connections and I can talk to my PhD students and see what makes sense. Okay. Yep.
Exam on the 22nd.
Yep.
How does an hour before, an hour
Usually I do try an hour before I give you a separate location.
completely or
Okay. And then you just turn in your camera and whatever. You got 1 hour like planning. Yeah. It's very helpful if you just remind me a couple, like a week beforehand. I know I have the letters. It's very helpful if you just remind me.
Sounds good.
Okay.
Email?
Yeah, that's okay.
I'm on the diff.
Is this like 3.85?
I am at below 3.85 right now. I'm on the diff. Last semester was not good because math 260.
Which one did, I don't know.
Oh, it's whatever you want to push, so, these are not my slides. Are these not? Okay.
Yeah.
I probably went over it too quickly. So you can push any values up there. So oftentimes pushes, like you just need extra register space because your function needs a lot of registers. And so you go and take all the, R4 through R7, push it up there, and then pop it back down when you're done. So so these are always going to be registers, is what gets pushed.
Okay,
And LR happens to be a valid register.
okay, so you just put the registers you want.
Yep. Just remember that the order matters. Okay.
Thanks.
Yep.
Thanks.
So, thing is, I was like all.
Oh, that's right, yeah.
Yeah, so thing is like, is there any ways like to make up like the class assignments for?
Sure. Go on the Piazza and answer multiple questions.
Okay, alright.
I look at Piazza as any way we're going to measure class participation, right? So you can do it through this, or just go answer a bunch of questions on Piazza.
Okay, alright.
Let's say if you missed a lecture, there may be 3 questions you have to answer.
Okay, alright.
Okay.
Thank you.
Yep.
So would you recommend when we're popping and pushing to the stack that we do it all at the same time? So like if we have to pop or push X amount of registers, we do it at the very beginning.
It's easiest. I mean, it's not always you don't always know what you're going to do, right? And on like an exam, I'm not going to, it's not that big a deal. But yeah, it's just way easier, especially if it's, it's just way easier to do it top and the bottom of your function and for your code.
Okay.
Does that answer your question?
Yeah, like just basically just do it all in one.